Alright, what's up guys? In this video we're going to pick up with some vector calculus, and we're back on the topic of line integrals. We're going to evaluate the line integral of this vector field. So we're given the vector field here, and they want us to evaluate the line integral of this vector field along the line segment from the point 0, 0, 0 to 1, comma 2, comma 3, where t is in between 0 and 1. So remember how we evaluate the line integral of a vector field. So we'll talk about it. All right, so there's actually two ways to write the formula, and I'll discuss both ways. So we got our line integral, f dot dr. Remember, that's just the dot product when you look at it. And it's just going to be the integral from a to b. And it's going to be f of r of t. And you'll dot that with the first derivative of r of t, which is r prime of t, and then integrate it with respect to t. So that's the formula for it. The other way that it's written that I do want to point out, because some professors may write it this way, but it's the exact same thing, and I'll explain why. So we got f dot dr is equal to the integral, or the line integral, f dot t of t ds. Now, how is that the same? Well, if you remember from multivariable calculus that t of t here is just the unit tangent vector. And remember, our unit tangent vector, that's just the first derivative of r of t divided by the magnitude of the first derivative of r of t, or the norm, some people may say. And remember that the ds part is just the magnitude of r prime of t. So if I were to actually plug this into the formula, you'll see it's the same thing. So we still got f dot dr. And if we plug this in, you see it's the exact same thing. Okay. Actually, it's going to be from a to b, and it's going to be the exact same thing. So let's take a look why. So we got our f of r of t, and let's say we got our unit tangent vector. So it's going to be the first derivative of r of t, all divided by the magnitude or the norm of the first derivative of r of t, multiplied by the magnitude of the first derivative of r of t. And as you can see here, the magnitude or the norm of the first derivative of r of t cancels out, leaving us with the exact same formula as this one up here. So that is why it's the same. I just thought I'd point that out because some professors write things differently, and I love doing that in my videos. There are many different ways in math things can be written, and a lot of times students could be looking at the exact same thing, just written slightly differently. So that was the reason why I want to touch on that. So bear with me on that. Okay, cool. And this could have been DT. Sorry. Okay, so let's go ahead and do it. So if we have our vector field up here, we know what dr is, right? So remember, dr, that's just dxi plus dyj plus dzk. And so if we actually go and stick that into the formula, you'll see how things work out. So I'll get another sheet here, and I'll move this one over the, well, put it right there because I need to see. So we'll take the dot product basically. So we'll have f dot dr. And you'll probably need a lot of room for a problem like this because it is a little involved. So we got our vector field, which was y sine of x squared, and then it's going to be I. And then it was plus xy z j, and then it was plus x plus y plus z k, and we'll take the dot of that with the dr, and the dr was dxi. Remember, ij and k are unit vectors, dimensionless vectors with a magnitude of 1, and then we got our dzk. Okay, now if we look at the line segment that we're given, it's going to be the line segment from the point 0, 0, 0 to 1, 2, and 3. So if we subtract away this point from that point, we're not changing anything. And so in this particular case, x will become t, y will be 2t, and then z will end up being 3t. And if we take the derivative, that means that dx is dt, dy is 2, and dz is 3. And you just got to plug it in the formula, basically. Okay, so we got f dot dr. And remember, t was in between 0 and 1. So you just got to plug everything in there. So it looks like we'll get 2t sine of t squared. And since dx was dt, all we got to do is stick a dt behind it. And then we'll have plus. And remember that for this part here, it was x, y, z. So x, y, z, that's t times 2t times 3t, which is 6t cubed. If we multiply that by our dy, which is 2, we'll get 6t cubed times 2, which is 12t cubed. So this would be 12t cubed. And you tackle on a dt behind that. And then the last one was x plus y plus z. Well, that's x plus y plus z. Well, that's just t plus 2t plus 3t, which is 6t. And if I multiply that by 3, I get 18t. So this becomes 18t. And then you tackle a dt behind that as well. And what you do is you split this integral up into pieces. So it's the integral from 0 to 1 for 2t sine of t squared integrated with respect to t. And then we'll, you can write it like this. Maybe this would have been a better way to write it. So let me do it this way so you can kind of see what's going on. And the last two are easy to compute. We'll go through and compute that one just in case you don't know how to do it. I'll show you step by step on that one. Again, that's just a fail safe, just in case you don't remember. Most of you guys probably already know how to integrate that, but just in case you don't. So let's just deal with the first one. The other two are easy, but let's just say you don't know how to deal with this one. The integral from 0 to 1, we got 2t sine of t squared dt. So how do we integrate that? Well, the first thing is 2 comes out front. I always encourage students to factor out constants because oftentimes they'll sit in the integrand and make the integral look far harder than it actually is. And that's really what we're looking at. Now, you may think integration by parts, but that's really not necessary. Now, if this were t times sine of t dt, then sure, integration by parts. But we can do a simple u substitution. There's really no need for by parts there. And because we know that the derivative of t squared is 2t, so it'll cancel out that t for us. So no integration by parts needed here. So du, that's 2t dt. And we get 1 over 2t du is equal to dt. So that means that we got a 2 out there, we got a 1/2, and we're going to change the limits. If we change the limits, they're actually going to remain the same. And this will happen periodically. The limits will remain the same when you need to change them. That happens from time to time. And it happens a lot more commonly with the 0 and 1s. But it really depends on what the u is. So that happens, by the way. So I just want to clarify that because when you do a u substitution for a definite integral, you have to change the limits. But if I didn't explain that quickly up here, that the limits actually end up being identical to what they were for t, you may think that I just brought the same limits down and didn't change them. I did, but they're the same. So I want to clarify that. So if we simplify the constants out here, that's just 1. And so really what we're looking at is the antiderivative from 0 to 1 for sine of u du, which we know is negative cosine of u, and evaluate it from 0 to 1. So that gives us negative cosine of 1. Cosine of 0 is 1, but since we have a negative, that's negative 1. Negative times negative is a positive, or a negative and a negative is a positive. So this becomes plus 1. Okay, and that's what the antiderivative would be for this first piece if we actually broke it up. And then the other two are obviously very easy to compute without having to do any work. So we got 12t cubed integrated respect to t. That's just going to be 3. And then we got the integral from 0 to 1. And we're asked to integrate 8t dt. And that's just 9. So essentially what we got is negative cosine of 1 plus 1. And these are both positive. So this would be plus 3 and then plus 9. Which essentially give us negative cosine of 1 plus 13. Which will be the answer. But let me see what that is. It's a decimal. Negative cosine. You don't have to write the decimal value, but sometimes it well, it looks like I'll just take 2 spots after the decimal. It'd be 12.45. So again, you don't have to write the decimal answer, but if you want to, you can. I got plenty of paper, so I don't care that I'm wasting a sheet just to put the final answer on it. So our final answer for this line integral, evaluate the line integral of this vector field. Our answer here is what we were evaluating, the line integral to vector field. So our answer to this is negative cosine of 1 plus 13, which is equal to 12.45 if you take 2 spots after the decimal. So that's the answer. Okay. And that's your final answer. That's how you work through the process. All right, so I got plenty videos on line integrals as well. So check out that video for more detailed examples as well. All right, that's it. I will see y'all next time.